Okay, we saw there were situations where soft margin wasn't going to help us, and so we're going to find ways of overcoming this problem, and a natural way to do that is using feature expansion. So what we can do, one simple way, is a standard trick, is enlarge the features by including transformations such as polynomials, right? So we started off with just, in this example, just x1 and x2. We can add in x1 squared, x2 squared, x1 cubed, x1, x2, and so on, right? Polynomial expansions. So you can go from a p-dimensional space, in this case 2, to a higher dimensional space. And the more transform variables you add, the more likely you are to be able to get separation in this higher dimensional space.
So I just noticed something. The m there, of course, is not the same m as we used for margin.
Oh,
so that's
good point, Rob.
Maybe we should use a different letter. Okay.
Okay, thank you. That was a bad choice of letter.
That's usually the kind of mistake I make. So I'm glad I caught you on one finally.
It's the kind of mistake I hate making. So enlarge a feature space and then fit a linear support vector machine in the enlarged space. And then when you project it down to the original space, it results in a nonlinear decision boundary in the original space. So for example, suppose we use degree 2 polynomials. So we'll use x1, x2, x1 squared, x2 squared, and x1 times x2. So that's a basis for fitting a general polynomial in 2 variables of degree 2. Well, in the enlarged space, the decision boundary would take this form. It's linear in the new variables, right? So there's a coefficient for each of them. So that was the form of our of a hyperplane. But of course, in the original variables, it's nonlinear because we've got squares and cross products. Okay, and this is what it results in for the same example that we saw. The decision boundary, you can see it's kind of split in two now. So remember, how do we get these decision boundaries? In the 5-dimensional space, there's a single linear decision boundary. Okay, and we can color all the points on one side blue and on the other side mauve. Well, if you project it down into this 2-dimensional picture of the original variables, this is what it looks like. So these are conic sections of a quadratic polynomial, and this is what they look like. And it's curious because in the 5-dimensional space, there's a margin on either side of the linear boundary, which are the dotted lines. Well, they also project down, and so there's a pair of margins for this piece of the curve and one for this. You'll notice these are nonlinear, and they even ends up in 2 pieces here. And importantly, in this case, this does a really good job in separating the 2 classes. Okay. Here's the equation. In this case, it's a cubic. We used a cubic polynomial in this case. So there's 9 transform variables altogether. And so it starts getting a little unwieldy. The dimension of the space is getting a little big here, but it solves the problem. Okay, well, so we seem to have a way of getting around these situations where we can't separate the data. Now, polynomials aren't the greatest choice, because especially in high dimensions, they get wild rather fast. We know, even in regression, we don't like doing polynomial regression with degree bigger than 3. And if you've got a large p to start with, and if you have a full, even cubic polynomial space, it's quite a large space. So it turns out there's a more elegant and controlled way to introduce nonlinearities in support vector classifiers, and this is through the use of what's known as kernels. But before we get into these, we need to understand the role of inner products in support vector classifiers. Okay, so inner products, if you've got a set of vectors, so we've got xi and xi prime. Now remember, xi is a p-vector. It's the set of variables for observation I. And xi prime is another p-vector. And this angle notation here means inner product between these 2 vectors. And it's just the sum of cross products of each of the individual components of the vector. So that's called the inner product between 2 vectors. And we write it in this compact way over here. So using that notation, we can write a linear support vector classifier. You can write it in this form over here. And And so here we have an inner product between each of the xi's in the data and the target point. So we're thinking of this as a function of a new point x, and it turns out you can write the support vector machine classifier solution in this form. Now you're not going to be able to see that just from looking at the formula for the linear function. This turns out to be how it comes out in the solution. But it's going to be important. It also turns out to estimate the parameters. So now we've got n parameters instead of the p, and n could be bigger than p. To estimate the parameters and beta naught, all we need are all the pairwise inner products between all the endpoints in the data set. So there's going to be an n by n inner product matrix. And it turns out that if we have that, and that's all we have, we can fit the support vector classifier and represent it in this form, and it's going to give us the same solution as what we had before. Now when you do that, what happens is that many of the alphas end up being 0. Right? So here we put hats on the alphas, and many of them are 0, and so the only ones we need to include here are the ones that aren't 0. And so we call those the support set or the support vectors. And so those are the alphas that are not 0, and each alpha is tied to one of the original points or vectors in the original data set. So we'll go back to slide 8 and see which ones those are. So let's get back here to slide 8. Here's slide 8. So which are the support vectors, or the points with non-zero alphas? Well, in this left picture over here, there's the 2 circle points. Those are support vectors. And also any points on the margin. So it looks like this one, and possibly this one. So in this case, there'd be 5 support vectors. So of all the points in the picture, only 5 of them would have non-zero alphas. And it sort of makes sense, right? Certainly the ones on the margin make sense because they define in the direction. But the ones inside are also going to define the direction, because remember, they have these little epsilons tagged onto them. And so they're going to play some role in the definition of the direction. In this one over here, there's 1, 2, 3, 4, 5, 6, 7 support points.
And just to add to that, right, if a point's not a support point, it means it's on the right side of its margin. And if we moved it, but we kept it in the same area, it's not going to affect the solution. So they're not support points. And one more thing to add, this is a kind of sparsity, but it's kind of a funny sparsity, right? Remember we talked about the lasso. It produces a sparse solution in the coefficients of the features. This is a kind of sparsity, but it's different. It's actually in the data space, right? Because now we're assigning a weight to each data point, and some of these weights are 0, and the ones that are non-zero are called the support points. So it's sparsity, but in the data space, not the feature space.
That's a good point, Robin. You know, and when you think of it like that, you say, suppose you had 1,000 points, and it ends up that there's 10 support points. You think, oh, great, you could have thrown away the other 990 points. Well, not really, because you had to have them all there to decide which ones would be the support points. Right. Once you found them, you can throw them away, but it doesn't really help much in the computations. Right. So it's a very interesting topic, support vector machines, and it took us a while to understand the details. Okay, so that's inner products. Now, what about kernels? So from what we saw previously, if we can compute the inner products between all pairs of observations, and if we can also compute the inner products between all the training observations and a new test point, then we can both fit the support vector machine and evaluate the function. Okay? So this can be quite abstract. First of all, an inner product is like a similarity. And so if you didn't really have data and you just had similarities, pairwise similarities between observations, in principle you could come up with a classifier. And there have been some interesting examples of that. So it allows us to be a bit more abstract. But more importantly, there's some special kernel functions. So a kernel function is a function of 2 arguments, in this case 2 p-vectors, right? So it's called a bivariate function. And these kernels compute the inner products for us. And you might not even know what the feature space is in which they compute in the inner product, but they can be thought of as doing that. But a concrete example is with polynomials. So here's a bivariate kernel function. Look at it. This part here is just the inner product between the original vectors, xi and xi prime. We add a 1 to it, and we raise it all to the power d. And it turns out that this kernel computes the inner product in a feature expansion space that we get by expanding these vectors, in these p components, into a basis for d-dimensional polynomials. Degree d polynomials. Well, that can be a huge space. If p is large and d is large, the number of basis function is actually p plus d choose d, which grows very fast as p and d grow fast. So that's a very big dimensional space potentially, but we don't need to actually visit that space because this function will compute those inner products. It's sort of like magic. You've got a kernel function that computes this inner product in this very high dimensional space. So try a little example with p is 2. So like in our example, we had 2 components in x and d is 2. And just expand this function and see what you get, and you'll see that indeed it does just what I said. And having done that, we can therefore compute the n by n inner product matrix for all the n observations by evaluating this function at each pair. And then we get a solution which is of this form, because again, k is computing the inner product between the target point x and each of the xi's in the sample. And once again, these alpha i's are going to be non-zero for only those points in the support set. So that's where the kernel comes into the support vector machine. One of the most popular kernels is called the radial kernel, and it's defined like this. If you know what a multivariate Gaussian distribution looks like, this is the important part of that distribution. It's a sum of squares between the components xi and xi prime, each of the elements. There's a gamma here, so there's a tuning parameter that's raised to the power e. And this is an inner product in an abstract infinite dimensional feature space. So this is a very high dimensional space, so high we could never visit it, yet this kernel computes the inner product for us. And we can therefore fit a support vector machine. And in our example where we had the 2 classes separating the mauve class, the 2 blue classes, this is the solution that it gave. And again, it seems to have done a really good job. Okay? So something's got a little weird here. How can we fit models in an infinite dimensional feature space and not be overfitting the data? Well, it turns out that even though it's an infinite dimensional feature space, many of the dimensions are squashed down heavily. In fact, almost squashed down to 0. So it's a very high dimensional feature space, but most of the space is squashed down. And the dimensions that are squashed down tend to be the more wiggly dimensions. The smoother ones are squashed down less. You'll notice if you went through this little example over here, you'll notice that it did give you the inner product between a degree 2 polynomial, but there were coefficients in front of these, and those are what give you the squashing factors.
So Trevor, in that example, in polynomial kernels, I could take d to be 1,000,000, right? And then I have a huge number of polynomial functions, which if I did with the feature expansion method, things would get out of control. So,
right.
So what happens here?
You run into trouble raising power
right.
to 1,000,000.
Yeah, with a polynomial kernel, I can get away with that.
You can get away with it, yeah.
And that's because of the squishing.
Because of all the squishing down, yeah. Okay, so a radial kernel is very popular, and it's one of the most popular kernels. It's used for nonlinear support vector machines. And there are other kernels, but this is the one people usually go to. And this gamma is a tuning parameter. And if you can think of it like the standard, it's like 1 over the standard deviation of the Gaussian. So if gamma is really large, it's like having a small standard deviation, and you get much more wiggly decision boundaries. Whereas if gamma is small, the decision boundaries get smoother. So we're going to take this machinery in the next segment and look at an example.